The problem is not just what motors are made of, it is where they are made and how fast they are assembled. Most consumers blame bad luck when a motor dies in 3 years. The real cause starts on the factory floor. These 5 secrets explain why 80% of new motors are garbage before they even leave the building. In 5th place, the speed over craft assembly line turns every minute saved into a hidden liability for the buyer. On today's factory floors, workers are paid for hitting quotas, not for taking care. Piece rate pay and output bonuses mean every skipped torque check, every missed drop of lubricant is money in someone's pocket, but a ticking time bomb for the person who buys the motor. Exponent's audit of a major Mexican supplier found that during peak production, lubrication was omitted on 34% of motors. Digital work instruction systems like Parsable and Line Pulse are supposed to catch these gaps, but timestamp audits reveal muted alerts and missing quality control steps, paper trails that vanish under the pressure of output targets. One former line worker described the reality. If you stop to double check a bearing fit, you get yelled at, you just keep moving. The result is a 4.2% spike in warranty claims traced directly to skip quality checks. In a teardown, a repair technician showed a misaligned bearing that vibrated itself to death in under a year, damage seeded by a rushed assembly shift. This is not bad luck. It is a system that rewards speed, punishes caution, and bakes early failure into motors before they ever leave the plant. In the 4th place, regulatory pressure and the so-called efficiency trap have quietly rewritten the DNA of modern motors. Over the last 20 years, a wave of energy efficiency mandates, like EU Eco-Design Regulation 2019-1781 and the US Department of Energy's upcoming MEPS, have forced manufacturers to squeeze every watt from their designs. On paper, these rules promise lower energy bills and greener grids, but the reality for consumers is a motor built on thinner copper windings, skinnier steel laminations, and a safety margin that has been shaved to the bone. Engineering change notices from 2022 to 2024 show copper mass cut by 8 to 12% per kilowatt, just to clear the latest IE4 standards. Lamination thickness dropped from 0.28 to 0.22 millimeters, all to hit the mandated efficiency numbers. These changes are not just theoretical. Finite element modeling predicts that a 10% copper reduction can push winding temperatures up by 4 degrees Celsius under real-world loads. In the field, overheating incidents climbed 4% after the 2021 rollout of stricter EU rules. The motor that survives a climate-controlled test bench now faces a daily gauntlet. Overloaded washers, pool pumps running through summer heat, and air conditioning compressors jammed in tight utility closets. The trade-off is baked in. Motors that pass the compliance test run hotter, wear faster, and fail sooner once they leave the lab. The efficiency trap is not just a technicality, it is a design compromise that consumers pay for with every early replacement. Coming to the top 3, the real killer is not just what is designed into the motor, it is what is hidden inside, thanks to counterfeit and substandard parts flooding the supply chain. Behind the glossy packaging and the compliance stamps, a forensic teardown often tells a different story. In 2024 alone, US Customs seized over 200,000 fake motor components, bearings, copper wire, even controller chips. Yet industry analysts warn that the majority still slip through undetected. These parts look right, fit perfectly, and pass the most basic checks, but inside, the flaws are catastrophic. A counterfeit bearing, for example, might be missing the micro-etched identification code or show a Rockwell hardness more than 10 points below specification. That is not a minor difference. Real bearings clock in at 260 HRC, while fakes can dip below 180. The result, early vibration, rapid wear, and a motor that grinds itself apart months and sometimes weeks after installation. Sample-based quality control is no match for this scale of deception. When only 1% of a shipment is inspected, Entire lots of subpar bearings and wire can sail through unchecked. Repair technicians open up failed units, expecting to find a fluke, but instead discover non-OEM bearings and copper wire with wild thickness variation, sometimes up to 20% thinner than specification. These are not isolated incidents. Field reports from auto repair networks and appliance service technicians confirm a surge in early life failures directly linked to counterfeit parts. Even the most careful assembly, even a motor that passes every regulatory test, is doomed if the core materials are fraudulent. The supply chain's blind spots have become a pipeline for early failure, and consumers pick up the tab, one burnout washing machine, pool pump, or AC compressor at a time. In second place, the reliability gap between lab testing and real-world operations stands as the industry's most quietly devastating secret. Manufacturers tout impressive MTBF, mean time between failures, pulled from standardized tests like IEC 60034-2-1. But those numbers are built on a fantasy. The tests assume motors run at steady load and perfect 25 degrees Celsius air, with humidity held at a laboratory minimum. Out in the field, the story is brutally different. Residential motors and washing machines, pool pumps, and air conditioning systems face daily thermal cycling, heating up to 80 degrees Celsius on a heavy spin, then cooling down overnight. Add in humid laundry rooms and cramped utility closets, and the stresses multiply. Field service data does not lie. Technicians log failure rates 2 to 3 times higher than the published MTBF. A dryer motor that claims 30,000 hours in the lab often limps to just 12,000 in a real home. Teardown photos from appliance repair shops show insulation delamination after only 500 cycles, with cracks spidering across the windings, damage that never appears in a climate-controlled test cell. One mechanical engineer who spent years validating motors for a major brand puts it bluntly: the bench test is a best-case scenario. It is not even close to what happens in a hot, damp laundry room. Even the industry's own field intake statistics confirm the pattern. Technician-logged failures outpace lab predictions by a factor of 2 or more. The validation system is blind to the cumulative effects of overload, condensation, and rapid temperature swings. As a result, the numbers on the box are little more than marketing fiction, leaving consumers to pay for a product that was never truly tested for the world it faces. This is the mechanism that lets earlier design flaws, subpar parts, and rushed assembly slip through undetected, setting the stage for the final reveal: the deliberate split between disposable consumer motors and the industrial-grade machines still built to last. The split between industrial-grade and consumer-grade motors is a calculated divide, built into every part and every warranty. Industrial motors like those found in Speed Queen washers, Pentair, and Hayward pool pumps, Leeson and Marathon drives are designed for the long haul. They use copper windings that are about 25% heavier per kilowatt, serviceable ball bearings, and thick steel housings. Their service factor sits at 1.15 or higher, giving them the margin to handle overloads and real-world abuse. These machines are expected to run for 20 to 30 years, powering laundromats, commercial pools, and factories where downtime is costly and reliability is non-negotiable. Consumer-grade motors, by contrast, are built to hit a price point and last just beyond the warranty, usually 5 to 7 years, sometimes less. Their copper packs are lighter, often a quarter less than industrial versions. Bearings are sealed and non-serviceable, pressed into thin stamped housings that cannot absorb vibration or heat for long. Service factors drop to 1.0, leaving no buffer for tough conditions. In practice, these motors run hotter, wear out faster, and fail early, especially in demanding settings like laundry rooms or pool pumps during a scorching summer. Teardowns reveal the difference instantly. Industrial motors fill their slots with copper, have bearings marked for servicing, and come with manuals that explain lubrication and rebuilds. Consumer models show less copper, no way to access bearings, and a parts list that signals planned disposability. Warranty terms reinforce the gap. Speed, Queen, and Miele offer coverage for a decade or more, while big box brands stick to a year or two. Pentair and Hayward pool pumps routinely outlast generic competitors by 2 to 3 times, with far fewer service calls. Leeson and Marathon are trusted in small business and farm circles for motors that just keep running. The numbers are clear. Over 25 years, a $150 consumer motor replaced 5 times, total $750. An industrial grade motor at $450 often lasts the whole span. The difference is not luck, it is intentional design. Across every hidden layer, one pattern is clear. Premature motor failure is not an accident. It is engineered by design, from boardroom mandates to factory shortcuts. The divide between disposable and durable is deliberate. For consumers, the true warranty is knowing which brand's still built to last. Next up, who actually does?